Hi everyone, this is Ms. Shea. Welcome to the first video lesson for topic 11. In this video, we will be looking at errors in data. After watching this video, you will be able to distinguish between qualitative data and quantitative data, discuss the differences between random errors and systematic errors in an experiment, their impact on the results, and how they can be reduced, distinguish between accuracy and precision in evaluating experimental results, calculate percentage error when the experimental result can be compared with a theoretical or accepted result. Let's get into the lesson. The qualitative data in an experiment includes all non-numerical information obtained from observations, not from measurement. These observations are made by using one or more of our senses, such as sight, smell, sound, or touch. Some examples of qualitative data you might record in the lab are color, change of state, production of a gas, formation of a precipitate, or release of heat. For example, we might observe that this substance is a black powder, or that this reaction produces a yellow precipitate, or that the endpoint in a titration is reached when the solution turns pink. Quantitative data are numerical information obtained from measurements. These data are always associated with random errors, also known as uncertainties, which are due to inherent limitations of the equipment used to make measurements or due to human limitations. For example, we may use an analytical balance to measure the mass of a sample. The analytical balance can measure up to the 10,000ths of a gram, and that determines the random errors associated with this mass measurement. We can use a stopwatch to measure the time a reaction takes to complete. The stopwatch measures up to 0.01 of a second, and that contributes to the random errors. But whenever we use a stopwatch, we have a delayed reaction time, so this also contributes to the random errors associated with this time measurement. Another example of quantitative data we often collect in the chemistry lab is volume of a solution. In this case, the random errors come from the graduated cylinder that we use. It is important to note that every measurement will have some errors associated with it. These errors can be categorized as random errors or systematic errors. We've already talked a little bit about random errors. Random errors are expressed as uncertainties, written as a range. For example, in the measurement 2.44 plus or minus 0.01 grams, plus or minus 0.01 is the uncertainty. Random errors cannot be avoided. This is because every measuring device we use has limitations. We can, however, reduce random errors by repeating a measurement. This is why we always want to do multiple trials of an experiment. A random error makes the measured value either smaller or larger than the true value. The probability of the measurement being smaller or larger than the true value is equal. So if the red line on this graph represents the true values, then the measured values in one trial may look like this. But another trial may look like this. Notice that the measurements are equally likely to be smaller or larger than the true values. The second type of errors is systematic errors. A systematic error causes a bias in a measurement in one direction. So the measured value is always smaller than the true value, or always larger than the true value. So again, if the red line represents the true values, the presence of a systematic error may cause our measurements to look like this. Notice all of the measured values are larger than the true values. Another systematic error may cause all of the measurements to be smaller than the true values, like this. Again, repeating the experiment will not solve this issue. So what causes systematic errors? Systematic errors are the result of flaws in the design of the experiment, incorrectly calibrated equipment, and consistently poor lab techniques. Not reading a meniscus at eye level is one of the poor lab techniques that can introduce systematic errors into your measurements. Let's look at how this might occur. If you read the meniscus in this burette correctly, meaning at eye level, the volume you should record is 20.00 cubic centimeters. But if you look at the meniscus from above, you'll get a volume that is greater than 20.00. It'll be around 20.60 cubic centimeters. If this is done consistently, then you'll have a systematic error in the volume measurements, with the recorded measurement always being larger than the true value. Similarly, if you look at the meniscus from below, you'll get a volume measurement around 19.70 cubic centimeters, which is smaller than it should be. And if you do this every time you measure the volume in the burette, then you'll always have measurements that are too small. Another example is not lining up the substance you're measuring the length of with the zero on a ruler. Here, we see that the recorded measurement would be 4.50 centimeters. But if we lined up the end of this strip of metal with the zero, we see that the recorded measurement should have been 4.65 centimeters. So consistently not lining up with the zero will cause a systematic error in which the measured value is always too small. Systematic errors affect the accuracy of an experiment, while random errors affect the precision. Accuracy describes how closely a measurement comes to the true value. Precision is the closeness of agreement between independent results obtained by applying the same experimental procedure under specified conditions. In other words, precision describes how closely repeated measurements are to each other. A way to think about accuracy and precision is to think about shooting darts at a target. The true value is the bullseye of the target. If I shoot 5 darts at the target, and all 5 miss the bullseye and are nowhere close to each other, then both my accuracy and precision are low. If all 5 of my darts hit the same area, but are nowhere close to the bullseye, then my accuracy is low, but my precision is high. If the 5 darts are all close to the bullseye, but are not close to each other, then my accuracy is high, but my precision is low. And finally, if all 5 darts hit the bullseye at almost the exact same spot, then both my accuracy and precision are high. When you repeat an experiment multiple times and get precise results, then we say that the procedure is repeatable. When other people repeat the same experiment and get the same results, then we say the procedure is reproducible. In some experiments, we can look up the value that we are trying to find in a textbook, reference book, or database. This value is called the literature value or the theoretical value. If we have the literature value, then we can calculate a percentage error to compare our experimental value to the literature value. The percentage error is calculated by finding the difference between the experimental value and the literature value, then dividing by the literature value and multiplying by 100 to get a percentage. Notice the absolute value bars, meaning that the percentage error will always be a positive number. The percentage error gives us a way to see how accurate our experimental result is. The closer the percentage error is to 0%, the more accurate the experimental result is. Let's look at an example of how a percentage error is calculated. A student determined, via a back titration using sodium hydroxide, the molar mass of an organic acid to be 130 grams per mole. The actual molar mass of the acid is 126 grams per mole. Calculate the student's percentage error. Since 130 is what the student determined in the lab, 130 is the experimental value, and the actual molar mass of 126 is the literature value. Plug these numbers into the formula, subtract 126 by 130, divide the difference by 126, then multiply by 100. Remember, we're taking the absolute value here, and the answer is 3.17%. So this student's experimental result is fairly accurate.